Okay, everyone, welcome to this next talk, Console Hacking 2013, by Sven, Martin, and Comics. Please give a warm round of applause to our speakers.
All right, good evening, and thanks for attending this talk. So as already mentioned, I'm Sven, over that's Comics, and that's Martin here. And we'll be talking about the Wii U. That's the Wii U, for those of you who have never seen it. It was released last year in November, and we bought it on the launch date, and it pretty much took us around a month to break most of the security it had. And that's essentially what we'll be presenting right now. As some of you may know, the Wii U is pretty much just an upgrade from Nintendo's previous console, the Wii, which was released all the way back in 2006. The Wii itself was also just an upgrade of the GameCube, released even earlier. We all have also been working on the Wii itself. Back then we were still called Team Tweezers, and we had a pretty good run. On the Wii itself. And because the security architecture mostly stayed the same, I'll be giving a very brief introduction about how the Wii was broken. For those of you who are more interested in the Wii itself, there's a talk at the 25C3 called Wii Fail, where it's explained in a lot more detail. So the first thing we did back then as Team Tweezers was that we used the GameCube compatibility mode, where you could only see a fraction of the RAM. Then we used a pair of tweezers directly on the mainboard to bridge a few address lines and move that frame around to be able to dump code that was left over from our full Wii mode. And back then, probably the most prominent bug was that they used a string comparison function to compare a binary hash in all of their signature verifications, thus rendering them completely useless. And what we did in the end was we built our own custom game-like channel on the Wii called the Homebrew channel, which is pretty much the most famous launcher used on the Wii. It's installed on around 5.2 million Wiis, and we later ported over to the backwards compatibility mode in the Wii U, and there we have around 27,000 installs as well. And yeah, so we did a really good run on the Wii. Let's see if we can do that on the Wii U as well. Just a quick introduction how the Wii looked like. It has a PowerPC processor running at around 730 megahertz. It's codenamed the Broadway. And on top of that, it also has the whole system on a chip that contains the rest of the hardware. And that thing was codenamed Hollywood. In there's the memory controllers. You get 64 megabytes of RAM, 24 megabytes of really, really fast RAM. And there's the old GPU called the GX, which is just a custom fixed function GPU that was also used back in the GameCube. And on top of that, they have a second co-processor in there, which is based on the ARM architecture and does all the security. We nicknamed that one Starlight because it's part of Hollywood. Right, so that's how the Wii looked like. Let's take a look at what they changed for the Wii U. The most important changes are marked in red. So as you can see, the PowerPC processor is now called Espresso. And instead of just containing one core, it now has 3 cores it can use. All of them have an individual L2 cache. One of them has a larger L2 cache than the other two. On top of that, they also upped the clock frequency to around 1.2 gigahertz. Then they added the gamepad of the Wii U, the thing you saw on the first slide. It looks like a console itself, has its own screen and so on. And if you're interested in that, there's another talk on day 3 done by Delworth. And that thing is called the DRH. There's still the old GPU in there, but that one's only used for backwards compatibility reasons. And the memory can be repurposed as some really fast on-die general purpose RAM as well. And this time the system on a chip is called the Latte because they want to stick with the whole coffee theme. And that's why we nickname the security processor the Starbuck. And now that I've talked about the hardware, there's also the software side. The games running on the Broadway are running on the bare metal. And there's no operating system, absolutely nothing except for the game itself. So there's no shared libraries, no linking, no memory protection, nothing. It's really just take the executable of the game, put it into memory, and run it. On the Wii U, they learned a little bit from the past, and they are running a custom Cafe OS on that PowerPC. It does real process separation, memory management, privilege separation, and so on. So it's really their own custom operating system running on there, doing its own part of the security. Now on the Wii, the security was all done on this Starlet. It was running iOS, which was also a custom microkernel only related to security, cryptography, and various I/O hardware. This is still true for the Wii U, so they have two parts that are taking care of the security. But it's significantly changed. It's been completely rewritten. It's a lot larger, and we've just called it iOS U because it's still performing most of the same tasks as the original one. Then games and software can be loaded either from a disk you insert in the console or from an integrated NAND flash. But RSA signatures were only checked when you installed a title on your NAND flash. If it was later run, there was no signature verification performed whatsoever. So as soon as you gained the ability to modify the NAND file system, you are able to run your own custom code and actually get a persistency as well across reboots. Again, on the Wii U, they learned from this. They added an eMMC storage for user software and games as well. But this time, whenever you launch an application, it will be signature checked. So you can't just put something on the file system and get away with that, or the iOS U running on the Starbuck will catch you doing that. One interesting thing about this is, this is the reason I've been talking about the Wii so much, is that the Wii U features fully backwards compatibility. So if you buy any Wii game, you can plug it into your Wii U and it will run it. And this is done, or we call this backwards compatibility mode the virtual Wii. And the interesting thing is that we have this software called the Wimpersonator, which all it does is it pretends to be a Wii, connects to Nintendo's update servers, and tries to get the latest software version, downloads them, and stores them on your computer. And we ran this even before the launch, and figured out that there's a new console type there, which was the backwards compatibility Wii mode. And while we couldn't decrypt any of the data that was downloaded because they changed all the keys around, we could see that the hashes of certain files still stayed the same. This was what you see in the bottom there, like info 00002 is already in cache. So this means that the Wii backwards compatibility mode is not emulated or anything like that. It's actually sandboxed. So they just turn off all the new hardware, then switch back to Wii mode, and it's running mostly the same software. There's been a few tweaks here and there, but we have the code for all of this. And iOS was also kind of like a Swiss cheese. So if you just looked at any kind of function, you would probably find an exploitable bug in there. So we could just use one of those old things to break into the virtual Wii. Just to understand at which point we break in, here's how the Wii looked like. So you had the Starlet, the security coprocessor, which would boot from boot 0. That's an on-die ROM, which can never be changed. It would chain load boot 1 and verify the SHA-1 hash against an hash stored in fuses. Boot 1 would then perform a full RSA signature verification on boot 2, which would later chain load to the system menu iOS. And only at that point is the PowerPC enabled. Before that, the Broadway, which is the PowerPC, was hold and reset. So until then the system menu boots, and it just performs a hard reset, jumps to the system menu. Then the system menu, which is like your default home screen, the user maybe clicks on some game he wants to play, and then iOS will reload to the one required for that game, and the PowerPC will be reset again. So all the handling is all done on the ARM CPU. The PowerPC is really only running the games itself. And since we're in the virtual Wii, we expected this to be mostly the same. The only thing we didn't know is how the system menu iOS eventually ends up running. We just know that it does end up running. And there's still the hard reset happening if the system menu boots. But there's been a small change. Because if you boot a game, it will not be booted directly. It will first boot a different title from NAND, which then chain loads the game. So this is odd, because it should be working mostly the same. But as it turns out, if we try to boot the PowerPC with our old code, we never get code execution. So we use the old thing, we reset it, point it to the right memory location, but nothing happens. And then if you take at the binaries that are launched by the new virtual iOS, they seem to be encrypted. And there are also 2 new encrypted binaries which are the special NAND loaders. And they can be booted directly. There's no decryption happening in iOS or anything. It really feeds those encrypted binaries to the PowerPC. And through just a little bit of experimentation, by trying to load those binaries, changing bits here and there, we figured out that the Espresso, which is the PowerPC with 3 cores now, will only boot if you feed it an encrypted and signed binary. So they added an additional layer of security there. You can't just take over the PowerPC as soon as you own the ARM processor. You still have to figure out a way how you can get in there. But this means that there has to be some kind of code running on the PowerPC that does all this. So there's an additional boot ROM on there. Because this format for the binaries is new and the princess is always in another castle, we call them the uncast images. So here just what I just mentioned, it checks how the boot process works. It checks if the target title is the system menu. If it is, it loads the encrypted one from the NAND. If it isn't, it will be proxied through those new special encrypted titles. Yeah, so this is how the chain of trust will actually looks like. There's an additional step for the boot ROM in there. And right, so there's an additional step for the boot ROM. Everything has to go through there. But what we can do now, we can break into iOS using one of those old bugs we still had around from the Wii days. And then we can just sit there, we can read all the memory. The ARM processor has access to the same memory as the PowerPC. So we can check what's happening while the boot ROM is running, because the ARM will be running at the same time. The first thing we noticed was that the signature and hash of the image is verified before it's being decrypted, which makes sense. On top of that, the image is decrypted in place from the beginning to the end. So if you observe memory, at first the first block will change, and then the second one, the third one, and so on until you reach the last one. And there's a third thing that's a little bit odd, because just before the entry point of your encrypted image, an additional PowerPC instruction will appear as the very last thing before your code is running. But this means, but if we can observe from the ARM, we can also try to see what happens if we try to overwrite some kind of memory while the boot ROM is running to trick it into doing something else. Again, the boot ROM, it verifies our ncast image, decrypts the image, and then it jumps to the decrypted image. So if you take a look at that decrypted image, for example, I'm just dumping memory, you will see that the very beginning turns back the Espresso into Broadway compatibility mode. So the boot ROM is running in full Espresso mode. If you reset the PowerPC for a hard reset, it will start as an Espresso. Then the boot ROM will run, it will run the Wii NAND loader, which will only at that point downgrade the whole thing to what it used to be on the Wii. And decrypting an image takes quite some time, because AES isn't really an insanely fast algorithm, and the system menu is a few megabytes large. So what you can do is you can race it. So you reset the PowerPC and wait until the very first instruction has been decrypted. So you just have a very tight loop that's checking, is it still the same, still the same, still the same? As soon as it changes, you overwrite the decrypted instruction with your own code. And the very first block is never verified again by the ROM. Just verifies the whole thing at the beginning. So this is a classic time of check to time of use. The result is you overwrite the first instruction, so that means you're on unsigned code. And on top of that, you're still in virtual Wii mode, so it should be a Broadway, but it isn't yet. It's still a full Espresso processor. Because the downgrading is only happening later, you overwrote that. And if you're in Espresso mode, you can just bring up the 2 additional PowerPC cores and use them. Now what this means, this isn't even an exploit. This is a complete design flaw, because the boot ROM is running on one processor, and it has absolutely no way of telling what that other processor that can be perfectly used as a glitching device is doing. As I mentioned, you can just use that ROM as an oracle to decrypt binaries, because all you do is you run it, wait until the last block is decrypted, reset the whole PowerPC again, and then you just dump memory. You get your full decrypted binaries handed on a silver platter for you. So the boot ROM is mostly pointless. It doesn't prevent you from re-enabling the cores. It doesn't hide any kind of code you shouldn't be seeing. It's just a minor annoyance. It's nothing there's no reason that it is there at this point. What we can't yet is decrypt Wii U mode binaries, but we don't have them anyway at this point. Obviously, it's no fun if we stop here, because we know there is a boot ROM, so we want to dump that thing. Yeah, let's just dump it anyways. The problem is that rebooting is really annoying on a Wii U, because you boot it up, it takes like a minute until it's there, then you click on the virtual Wii, it takes another minute, and so on, and so on, and so on. And every time you make a single mistake, which is bound to happen when you're trying to hack something, this can really add up a lot of time. So we've been trying to build a remote agent from the PC, which is what we're always doing when we're hacking some kind of a meta device. So what this really is, you build a serial port between the console and your computer so that you can send RPC commands from some Python script over the serial port to the console so that you can really interactively hack the console directly from your computer without having to compile a binary and reboot that thing over and over and over again. This is really nice because it cuts down your whole development time. But there's a small problem because we can't communicate yet. You have no serial port. On the Wii, we could just use the memory cards. It used to be just a SPI bus, so we could just plug in some custom hardware and we had a full serial port. But those are gone now. So we started with something we call LOL serial. I mean, the picture pretty much shows what it is. You can turn on and off the serial, the sensor bar, which is just a bunch of infrared LEDs. You can turn them on and off from our code. So you can just bit bang serial over that power line. It's really slow. It's only an output, but it's good enough for you very early printf debugging. Let's take this a step further with this really awesome thing called get2HCI. So this is a really, really questionable OHCI stack. It essentially supports one single FTDI device that should already be plugged in when it's running, and otherwise it will just completely fail. It can also only send one type of messages, but to get a bidirectional I/O working. You don't even need to open your console. You just plug it into the Wii U's USB port, hook it up to another FTDI chip, hook that up to your computer, and you have your serial console. But that's still slow. And even worse, we didn't even open up our console yet. Our warranty is mostly still intact. So let's use our final solution, which is the GPIO Gecko, and that's the one we're still using today. The USB Gecko is an old device that we used on the Wii. You could plug it into the memory card slot. This time we just found some random GPIOs on the mainboard, and we're now bit-banging the Wii's memory card protocol over those GPIOs so that we can reuse the old hardware to get a really fast serial console. And most importantly, the warranty is finally void. As I mentioned, we want to dump that boot ROM. This is why we did the whole thing with the serial consoles. And I also mentioned that one instruction that appears just before the decrypted code. And for those of you who are not familiar with PowerPC, this is a move to special purpose register instruction. And a special purpose register, it makes a lot of sense to contain a bit to disable the boot ROM. So our hypothesis is, which later turned out to be true, that this single instruction there will disable the boot ROM. So can we just use the same approach we used to get to get the PowerPC in espresso mode. Can we use the same approach to dump the boot ROM? Turns out that that sadly doesn't work, because no matter how hard we try to raise the ROM, the PowerPC will always execute the original instruction. We even wrote a very tight hand-assembled assembly loop, and it still would just disable the boot from that. Where it turns out there was absolutely nothing we could do at this point anyway. Because in order to understand why this didn't work, we're going to cheat a little bit and explain what the boot ROM is doing first, and then how we managed to dump it. And that's Martin's part.
Okay, so I'm going to take you through a boot ROM walkthrough. The boot ROM does some really interesting tricks with memory management and cache management, and it's almost a little piece of art the way it does things. So this is going to touch into the intricate details of PowerPC caches and PowerPC memory management. So hold on to the right, this is going to be interesting. So we're interested in looking at mostly memory management. So we're going to have 4 columns here. We're going to look at different parts of memory, different addresses, what the data is in RAM, the physical RAM chips, what the data is in the CPU's L2 cache, which may or may not be the same as RAM, because the Wii U is not a cache coherent system, so there may be times when these two do not match. And then the PowerPC CPU has 2 operating modes. It can operate in real mode, where virtual addresses correspond to physical addresses, so there's no address translation. Or it can operate in translated mode, which is when the memory management unit is turned on, and there can be arbitrary mappings between where the addresses that the code uses and the addresses in physical memory. So let's set the stage first. We start up with the binary image for the system menu, or whatever the uncast image is, at that address there, 0133 foo. And we have at offset 0 is the header for that, and at offset hex 100 is the start of the ciphertext. We're also interested in address 0 because that's where the PowerPC exception vectors are. It's also where the reset vector is. So let's look at what happens there. But to start with, there's nothing really in that area of memory. So first, we hard reset the PowerPC, and it comes up in real mode, like every other PowerPC. And the first thing that we notice is that in real mode, the PowerPC is executing the boot ROM, not memory. The boot ROM is built into the espresso, and it overlays memory at address 0. So whenever it fetches instructions, it will do so from the boot ROM. There's no MMU setup yet, so there's no translated mode. The caches are off, so it's pretty simple. And you can also see how the system menu encrypted blob, the uncast blob, maps to real mode. The first thing the boot ROM does is it clears the MMU, the caches, the registers. It wipes everything to get a nice clean slate. Nothing interesting there. And then it maps the boot ROM using a PowerPC feature called the block address translation. The PowerPC has a memory management unit, and it can either map things using the usual page tables, which can do complex mappings, but it has a very simple memory mapping feature. The block address translation is just a bunch of registers that say, take a big block of memory here, map it to a big block of memory there. It's really stupid, it's really easy. So it maps itself to translated mode with this feature of the espresso. It also maps to other sections. It maps address 20000 to that 160 address there, which is in the middle of RAM. There's nothing special about it. I don't know why they picked that. And there doesn't seem to be a reason for it to map this, but it does. We'll see in a second why. And it also maps E000 blah, blah, blah to the same location. And that's not even physical memory. That's an invalid address. So that makes no sense, but we'll see what happens. Then it switches to translated mode. So now it's running in translated mode, still running the ROM. And this is when it enables the caches. Now you'll notice the really interesting thing here is the L2 cache column is now clear because that's initialized and empty. But in real mode, suddenly we get the reset vector instead of the boot ROM. So we're leaking main RAM from the actual RAM chips to real mode. The reason for this is because the boot ROM is special. It only works when you perform uncached memory accesses. So if there's a cache in the way, you don't see the boot ROM anymore. And the reason why it works in translated mode is because when it set up this BAT mapping, it did so with caching inhibited. There's a bit called the I bit. And that forces it to keep bypassing the caches for the boot ROM. But in real mode now, we're back to main memory. It also enables a feature of the Espresso that goes way back to the GameCube days called the locked L1 cache. The L1 cache is 32 kilobytes, split it down the middle, and it sets up 16 kilobytes as a dedicated on-chip memory that only it can see. It's only useful for data. So now it has 16 kilobytes of private RAM mapped at this E00 thing, which explains that. Now, the next thing it does is it sets up exception vectors that just infinite loop in memory. It uses a temporary mapping for this. And the reason for this is that in case something happens and it ends up executing an exception vector in RAM, it doesn't want to fall through and execute code from a random place in RAM. So it just sets up instructions that jump to themselves at that address, and it's an infinite loop. So now, up until this point, the boot ROM is running with no stack, no nothing. It's all hand-coded assembly, really low-level stuff. Now that it has memory that it can use privately, it sets up a stack, copies its data sections, gets prepared to run real code. But before this, it copies itself. And the reason why it does this is because the boot ROM now is running in uncached mode, because it has to be uncached. But it's a crappy, slow boot ROM that isn't, very far removed from the cores. You don't want to be running crypto code from a crappy slow memory. That'd be terrible. So it makes it a copy to this address, 20000. And you're thinking, well, that's going to copy the boot ROM to RAM. But it doesn't, because when it copies itself to that address, it mostly ends up in the L1 cache. Because the cache, of course, will try to cache the values before getting them evicted to memory. Then it uses a really neat trick to flush that L1 cache into the L2 cache. It basically just writes a bunch of garbage to the L1 cache that is guaranteed to evict all the cache lines, send all that data over to the L2 cache. But it can't just flush it with a normal flush instruction, because then it would load to RAM, and we don't want the boot ROM to end up in RAM. So it's using this really hacky trick to keep itself from going to RAM while using the L2 cache as memory, which is not designed to be used as memory. And then it just jumps to this new location, and that's what starts doing the main execution. It copies the AES keys from the secret fusers or OTP to its private memory. It disables those keys to make sure nobody ever gets access to them again. It will hash and decrypt the image. And the really interesting thing here is that it can't just read it, because it would end up using the L2 cache. So it goes back to another feature of the GameCube, where it has a DMA engine that can copy data straight from external memory into and back out of its locked L1 cache without doing anything else, without going through the L2 cache or anything. So it's moving data between that red square there and on the bottom right corner where there is a DMA buffer. So it does that with a header, it checks the signature, then it hashes and decrypts the ciphertext, and it's doing this by ping-ponging data through the locked L1 cache, bypassing everything else. So now it jumps back to the boot ROM, it's done. Presumably the hash check succeeded, so if it doesn't, it just locks up. And now that everything is ready, it can clean up. It jumps back to the boot ROM, not the copy. It wipes this section where it was keeping its own copy of the code. And it makes sure that gets wiped in L2. It wipes its data in locked L1 cache. It unmaps all of this. It's just undoing, basically, the startup process. And finally, it maps the payload. So up until this point, the ciphertext or plain text section wasn't even mapped in translated mode, so you couldn't see it except through this DMA system. But now it's mapped. And the next thing it does is it disables and invalidates the L1 and L2 caches. So now all the data that used to be there is completely gone. And now is when it writes this special boot ROM disable instruction. It writes that makes it through to the L2 cache, and it flushes it to make sure it makes it out to RAM. It jumps there, and at the point where it hits this instruction, the boot ROM is disabled permanently, and it starts running the payload code. And this is why you can see why overwriting this instruction in RAM did not work. Because even if you overwrite this instruction in RAM, it's still in the L2 cache. The plaintext is not in the L2 cache, because we DMA'd that. So if you erase it there, you can gain execution. But that one instruction at FC is in the cache. It doesn't matter what you put in RAM, it still runs the disable instruction. So this is really clever. And it actually writes it and reads it and verifies it, makes damn sure it's in the L2 cache. So this is a really clever trick. I mean, it's kind of a horrible hack, but in a way, it's really cute execution. It keeps the ROM isolated, but there's a hole. The PowerPC has two external reset lines. One is called H reset, which does a full hard reset of the chip, runs the boot ROM again, it's like starting from scratch. The other one is sreset, which is a soft reset. Basically, this is really just a non-maskable interrupt. It just makes the PowerPC take an exception to its reset vector, but it doesn't really clear anything. It doesn't re-enable anything. Both of these are controlled by the starbuck. They're just bits in a register we can turn on and off to bootstrap the PowerPC. They're separate bits. So we come to the sreset hap. What happens if we assert sreset, if we reset the PowerPC, the Espresso, while the boot drum is running? Well, if you just pick a random point, let's say when it's hashing and decrypting the ciphertext, we assert sreset. Whenever it takes an exception, whenever you get an interrupt, or in this case, a soft reset, it switches back to real mode, but it's got this annoying infinite loop instruction there. So all that's going to happen is it's going to get stuck in an infinite loop. Even if we change RAM, we make it jump to our own hack code, to our own dumper, whatever, it's still in the cache. So we have the same problem. It's still going to get stuck in an infinite loop no matter what we do to RAM. But what happens if we wait a little bit? So at some point, the boot drum is disabling and validating and re-enabling the L1 and L2 caches. So at this point, the L2 cache is empty. If we change RAM to jump to our dumper code, suddenly that's visible in real mode now because the cache doesn't have that data anymore. Then we assert sreset, and then the PowerPC jumps to our code, and since the boot drum is still mapped, we can just read it. So this happened 8 days after the release, by the way. Unfortunately, it's too late to get the keys, the European release, just to make sure we're on the same page. But it's too late to get the keys because the OTP is already disabled, the locked one is already wiped, keys are gone. We want the keys. So let's look at the other reset line. It's called hreset. It resets the whole Espresso. It restarts boot drum execution. hreset is level sensitive, so you bring it low to start resetting the PowerPC. It does whatever it needs to clear, clears internal state registers, all that fun chip level design stuff that I know nothing about. And then you release it to begin execution. The datasheet for the PowerPC 750CL, which is really close to the Broadway used on the Wii, and presumably close enough to the Espresso, says that hreset must be held low for at least 255 bus clock cycles. What happens if we try narrower pulses? So the starbuck runs at the bus clock rate, coincidentally, and it can control hreset with single cycle accuracy, because one NOP on ARM9 is one cycle. You can make a little timing loop. So we fill all RAM with jumps to our dumping code, just to make sure that if anything weird happens, hopefully it goes to where we want. Remember, we're doing this Python thing from a PC. We don't want to be timing hreset from a Python script. So we upload a little snippet of ARM code to do really accurate cycle level hreset timing, disable interrupts, all that fun stuff. Then we start the PowerPC normally, just to make sure it's into a sane state. And then we hreset it right in the middle of the boot drum. It doesn't actually matter that much where. We try different widths for hreset, see what happens. And we hope that at some point, something will blow up, it'll screw up, and it'll end up jumping somewhere in RAM and run our code. And then something will happen, hopefully, and then we get profit. So, what happened? Well, the PowerPC crashes if we do a very short period. For a very long period, it restarts normally. If around the middle, it just fails and deadlocks. But for one of two specific pulse widths, really weird stuff happens. And the widths vary from unit to unit. It's an analog thing. It seems to be running our code, because we got some response from our dumper. But let's look at a cat version of the PowerPC. So it's running, but something screwed up real bad. It's skipping instructions. Sometimes it doesn't issue writes to memory. Like, we're dumping stuff, and there's stuff missing in the dump, and it's like the registers are offset, and some of the values are weird. It looks like some functional units in the core are totally fucked up. I have no idea what's going on, but it's really fun. It's running our code. But drunk is good enough. Because all we have to do is read each keyword and write it to memory 4 times and cross our fingers and then look, that one, that one, that one, that one. And we have our keys. So that was 11 days after the EU release, and that's a hash that we posted. It's a hash of a linked file, which has the hashes of the keys because we must go deeper. So the espresso is pwned in virtual Wii mode. Time for the Starbuck in Wii U mode. The Wii Starlink has boot 0, which is this boot ROM that boots the Wii. The virtual Wii doesn't have a boot 0 because it runs from Wii U mode. How does Wii U mode boot? We have no idea. We can't find out from virtual Wii mode. Or can we? So on the Wii, boot 0 was mapped to that address. It gets disabled by boot 2, not boot 1 for some reason, by writing to a hardware register. That register is not clear only. You can re-enable that register. Probably see where this is going. It still exists in Wii mode for compatibility, because iOS clears it and all that stuff. What happens if you set the enable bit again? While boot 0 appeared, it does not look like the Wii boot 0. I don't even know what the hell they were thinking. This is just ridiculous. It just shows up. And we found this out 14 days because, we didn't think they'd be that stupid. So that's the hash we posted. Okay, the Wii U boot 0 is much more interesting than the Wii one. It does real signature checks. It supports booting a recovery image because the Wii was notoriously breakable, and they just throw away motherboards and put new ones in when they break them. There was no recovery mechanism. But unfortunately, we haven't found an exploitable bug in boot 0. At least yet. So this is all we have for Wii mode. Now let's look at Wii U mode. And I'll hand it over to Comics for that.
All right. So, according to the paper that just got pulled up, it doesn't seem we're getting the full hour here, but I'll try to hurry here. So, how to pwn Wii U mode. So for virtual Wii mode, there was a lot of reference to go on. There was all the old software, and we could see how it changed. There's the hardware, all of that. But that was only able to go so far. So in order to pwn Wii U mode, we had to do it just like any other console. That is by treating it as a black box. So how do you hack any embedded device? Well, any large embedded device with a user interface that's vaguely modern? Well, you go after the web browser. Because just about everything uses WebKit. WebKit is LGPL. They have to provide the source. You can go get the source. It's not like we care very much usually about what's actually in the source. It's usually almost identical to some version of SVN, but we can look at the changelog and see, well, how old is this? And because WebKit has vulnerabilities fixed constantly, so if it's old, and for embedded devices it often is, we have a huge menu to select from. So the last changelog entry from the open source version of WebKit, as for the release that was current last year, the end of 2012, is from 2011, October, so it's a year out of date. In theory, there should be a lot of vulnerabilities. So how do we actually find these old bugs? A lot of them are reported, but they're also kept secret. In fact, well, with some other projects, once the bugs are old enough, they get deprotected, the public can view them. For WebKit, that doesn't seem to happen. It's still, all those old bugs are still restricted. But the bug numbers are mentioned in SVN commits with unit tests for what used to crash. Oh, what did I do? I pressed B. Help. No. Okay, so all we have to do is grep the SVN log for bugs, and we try to view all these bugs in the bug tracker, and which ones are we not authorized to see? Those are the interesting ones. Not a new idea. A lot of people are doing this, but this is the first time I'd done it. So to Nintendo's credit, they did recently, a few months ago, they updated WebKit to a version as of late 2012. So now it's well, it's about the same amount of out of date as it used to be. Now, that doesn't mean that exploitation is necessarily easy, because we don't have, there are a lot of things we don't have. We don't have crash logs, for one thing. With some platforms, in fact, a surprising number, they'll just give you the crash log, and then you can sort of see what's going on. We don't have that. Structure and vtable layout, we don't really know anything about the compiler. We might be able to find out, and there's some amount that you can get from the source code, but it's still limited. Like if you have a use after free, you're often going to want to overlap the one vtable with another, and like the wrong function will be called, but we don't really know what's going to happen there. We don't know about the allocator, so for a use after free, the behavior of the heap depends on the precise algorithms used by the allocator, but we don't know about that. So, although it's certainly possible, I mean, once they used an old WebKit version, Nintendo pretty much guaranteed that we were going to get code execution this way eventually. And you could consider this a serious flaw. I mean, a serious lapse in security. Even if WebKit, there's going to be vulnerabilities eventually, but by making it easy to find old vulnerabilities, you're pretty much guaranteeing that code execution is going to be achieved pretty soon. Now, in a good, well-designed security system, whether the Wii U counts is debatable, but there's many layers of security, and just compromising the web browser isn't going to give you that much, but it's still going to give you infinitely more than just poking at the user interface. So you really should try to make this as hard as possible, and they didn't. But anyway, as saying, there are many bugs to choose from, and there are plenty of hard use after frees and overflows and all this. But I found a nice heap overflow that let me overwrite a pointer to an array buffer view or something, and then that let me specify an arbitrary address, and I could dump memory. And then we got to look at the Cafe OS in IDA and giant database file, because IDA has giant database files. And it was a dump of all the modules loaded into memory at the time. So how does it compare to the old Wii OS? Well, this has been partially covered earlier. As said, no longer running on bare metal on the PowerPC. It's running under a kernel. This is necessary for one thing, for process isolation. The Wii U can actually run multiple things, multiple applications, like you can run the web browser while a game is on. Another reason to do this is that there is kernel-enforced no execute, or data execution prevention. So on the Wii, everything was just read, write, execute. On the Wii U, not only is non-code not executable, you can't jump to it, but the kernel enforces this, so you can't just say, hey, here's some memory, I want to M-protect it, prod exec. No, it won't let you do that. With a special exception for the web browser. This interesting policy is shared with the iPhone. It is this way because web browsers need JITs to run fast, and for JIT you need to run code, and so there needs to be a way to do that. But it's somewhat paradoxical. So, downsides, or missing things. No ASLR. It's 2012 was when it was released, and there's no ASLR. There are also lots of bugs. On a cursory examination, it seems to be there turned out to be a lot of bugs in various levels of the operating system. This isn't exactly a security measure, like some kind of mitigation, but it means that it wasn't carefully audited. And that could be considered a very important mitigation. So in general, this reminds me of like last generation of consoles, like the Wii U is in some other ways. Like the PS3 also had no execute, and it had no ASLR, but I think that the newer ones are better on that, so unfortunately not this one. So another interesting feature, not exactly a security measure, but As previously mentioned, the Cafe OS uses dynamic linking for everything. The Wii used just static linking, plop everything, the whole SDK into every game, plop it into memory. This feels more like a real system. In fact, it almost uses ELF. The binaries look like ELFs, except there are some gratuitous differences. Like the sections are compressed with some custom thing, and the symbol tables are all different, and it's changed to be sort of more like the Windows linking model for some reason, and it's all different. But it's close enough, so I guess they get credit for that. So benefits are function names are visible. For reverse engineering with the Wii, there was some leaks of function names in some weird cases, like some symbol map got onto a disk once, and but those were closed and those were out of date. For the Wii U, they're just always going to be function names visible, always useful whenever you need them. Separated, functionality separated by library, so you can sort of see what does what. And this is a bit of a historical note, but I'll be quick. For the Wii, there was eventually a port of Linux, but since that didn't run very well, since there wasn't very much memory on the Wii, and most people just used libogc, which is a custom library which sort of did the same thing as the SDK, but unfortunately it didn't only do the same thing as the SDK, many of the functions were just lifted straight from the SDK, like manually translated from assembly to C, and there were eventually worries that this would be a copyright violation. It's hard because you have these random register rights. You can try to figure out what they can do, what they actually do, and maybe have some nice functionality, or you can just copy them, and there are a lot of them. Anyway, this avoids the need for that. Anyway, so while Markan was doing all the stuff with reset that he mentioned, because once he got the keys, it was possible, the keys he dumped included both the Virtual Wii and the Wii U mode keys for the PowerPC. So since it was pretty easy to end up reading data from the file system, that meant that I would have been able to use that potentially to decrypt the PowerPC kernel and be able to see what's in it and find vulnerabilities white box rather than black box. But I didn't know this was going to succeed. It hadn't been done. So I decided to try to dump it with a blind exploitation. So, pretty basic stuff. I tried to pass a bunch of syscalls that take addresses and do something with them. Memory addresses, I tried to pass invalid addresses and see what they do. Most of them, they just returned errors or did something predictable. One of them froze. Some addresses worked that were not accessible normally. And basically, it was a straight read from the kernel. It took the pointer and read it without doing any kind of check. It printed it to a log. You could get the log with some other way to do it. So I printed 1 byte at a time, checked the log, and very slowly dumped whatever kind of data from kernel space that I wanted. But data, not text. No matter where I tried, and I could not get any text. And there's a reason for that. As previously mentioned, there's both page tables and block address translation, but interestingly, the BAT registers are completely separate for instruction and data. They're just separate registers. This is useful for one thing. It's usually used to implement no execute for this memory because you can just put it in a data BAT but not an instruction BAT, and then it'll only be able to read it with a data fetch. But the kernel did the opposite. It only mapped it in instruction BAT, not in a data BAT. So if you try to read from this memory with some load instruction, it won't do anything. That means you can't have any data in text, which a lot of other systems use for various things. But it means that that's a pretty interesting security measure because you can still run it fine, you just can't dump it. The one thing is that I'm not quite sure whether it was intended as security or just because they were running out of BAT registers. But, well, that wasn't enough though, it was nice, but eventually I was able to find a way to write data, and then I was able to do some DMA thing to dump the kernel, and it got all this nice stuff in IDA. This was useful for a few hours, I think, about that, and then Marcan showed up on IRC saying, oh, I got the key, and then the whole thing became useless, but, well, it was fun. All right, so quickly about iOS, which, as mentioned, is running on the ARM processor, which incidentally makes it automatically 5 times easier to reverse engineer because hexrays works on ARM. I'm not sure whether that's a good thing or a bad thing. So I tried to blindly exploit the iOS userland. iOS exposes, like it did on the Wii, a sort of /dev Unix-like interface with like IO control calls and something like that. I managed to do something. I got some ROP, fun stuff. From there, I tried to exploit a different module that was only accessible from within iOS. And then I did some random call to some IO control in the crypto module, and then my Wii wouldn't turn on. You know, I wasn't expecting that. It was stay away from like NAND writing, any kind of that, but it's just, oops, your Wii's bricked, sorry. So I had to sit out for a while, but until I borrowed someone else's Wii U and promised very much not to try anything like that again. But eventually, I was able to exploit the iOS kernel. And once we got code running in the iOS kernel, we were able to dump the OTP, or almost all of it, which contains a bunch of different things, including the common key, which is the key needed to decrypt what you can download from the internet into what goes on the file system. So now there's no need to like anything on the PowerPC or anything that's not separately encrypted. You can just download it. And also the virtual Wii, because all the updating and downloading for the virtual Wii actually happens in Wii U mode, and the Starbuck and cast key. So that's pretty much everything except for one thing.
So there's one thing missing here. So we mentioned that the OTP, we managed to dump most of the OTP, but not all. There's a boot1 encryption key used by boot0 to decrypt boot1. That's disabled permanently, separately, early in the boot process, and there's no way to get it back. We haven't found a way to get this key yet. We're trying some really cool stuff, some side channel attacks. Expect to hear from us if we are successful, but so far, we don't have it. What about other approaches? We don't care about Wii U software. All we want is access to the hardware for homebrew. So the question is, can we escape the virtual Wii sandbox and go back and enable Wii U hardware so we can use it? So this takes us to Cafe2Wii. Cafe2Wii is the name of the Wii U Starbuck code that switches to virtual Wii mode. It contains interestingly low-level code. It's really cool because it doesn't have iOS, it doesn't have a kernel, it's just low-level code. It has all the modules it needs. It's very dense and useful information and code to reverse engineer instead of a bunch of like system call crap that we don't care about. It tells us what we have to undo to go from virtual Wii mode to Wii U mode. And now that we have the keys, the Wii U and cast key and the Wii U common key, we can just download it and decrypt it. But Nintendo had a holiday gift for us last year. When we did this, we found Cafe2Wii is an ELF executable, of course. Run file on it. It's an executable, statically linked, not stripped. This is the only unstripped binary that I found, other than the Cafe OS linking stuff. And so yeah, they left the symbols in, and they left full dwarf debugging information, including all the structures. Plenty of strings. Apparently they call MCP, the thing that does the system control and security stuff is called MCP, so someone likes Tron over there. There's the C2W section, which is the Cafe2Wii main, the main file, the main object file there. And there's a bunch of really cool symbols. MCP, hardware set AHP compatibility mode, set compat mode, set mem1 compat mode, set sysprot, which is a really interesting register, launch Wii iOS, finalize Cafe, which is kind of the last thing that happens before Wii mode. and set espresso PLL config GPIO, which is what presumably switches the espresso frequency multiplier and does the espresso speed. Also, apparently they use Sigwin. Unfortunately, this was a mixed bag. The sandbox is a little bit leaky. We can partially reconfigure the bus to Wii U mode. We can half enable the extra 8 megabytes of Mem1, but it kind of breaks Storybook at the same time because the bus is messed up, so it's not really useful. It shows that it's there, but it's not actually usable by Homebrew. And we can mess with some GPIOs. We can change the fan speed and some other miscellaneous crap. But unfortunately, that's not enough. Most of the new cool hardware, the new GPU, separate USB controllers that let you talk to the gamepad, all that fun stuff, that's all clock-gated and powered off. And the registers that you need to turn that back on seem to be locked off by something called sysprot, which is one-shot and cannot be reset as far as we can tell. So I actually tried flipping every bit in every register in the whole area to hope that something would let me, it would turn on and let me change things, but no dice. So we tried, but unfortunately that won't work. It would be possible for Nintendo to enable a homebrew sandbox that turns off the Wii U, say, file system and security and keys, but it lets us use the hardware while keeping their DRM safe. This is kind of like other OS, and it would be better than other OS because other OS depended on a hypervisor, which is of course riddled with bugs, while this uses hardware lockouts, which are fairly solid. Unfortunately, Nintendo is not interested in this. As far as we know, anyway. So we have a little bit of an epilogue. I wrote a blog post about this. And so, at this point, we've broken most of the security, but what remains is the work to develop the open frameworks. We need to write an SDK or port Linux or something like that. And we thought we were going to do this, and then we kind of sat on it and like, yeah, maybe tomorrow, maybe tomorrow. No one seemed to be really interested in it. And the thing is, there's an internal clash between the homebrew community and those interested in pirating games. Back in the day, when the consoles were simple, you just ran your own code and started poking registers, and it was all good fun. These days, you need a lot more code to do interesting stuff. Meanwhile, piracy is, you patch the function to load code from disk and send it somewhere else, and you can pirate games. So piracy almost gets easier with complex OSs. Homebrew gets harder. And this is kind of the conclusion that we reached, that it's possible that the return on investment isn't really worth it anymore on Homebrew, because it takes a lot of work, and meanwhile you get to watch people download games the moment you get the code execution, because someone figures out, oh look, DVD read, how about I redirect that to flash read or to USB read or something like that. It's usually pretty stupid. The PS3 loading stuff is like a few bytes, a really short function. So, with the Wii, it's really cool because everyone has a Wii and it's connected to the TV. With the Wii U, people have smart TVs, the Steam box is coming out. There's a lot of more open, easy-to-use devices that you can hack. So this is kind of the question, right? Is it worth to continue with this? I don't know. But what I do know is that we set out a challenge to tell people that we wanted to gauge interest and see if they could port Linux to the 3-core espresso, which we could enable with that really trivial design flaw. And that's for 46 pages on this forum thread. I mean, they're trying, and I give them a lot of credit for trying, but they don't have the kind of people to really pull this off in a reasonable amount of time. We haven't really seen some PowerPC kernel developer or some old school homebrewer say I'll do this, I'll get this working, and I really want to have Wii U homebrew. So this is where we are today. Thank you very much.